Hi guys, Sajjad Hussain again with a new video. In this video I am going to solve a problem which is here in PCA note 31808. It's chapter 29. Let me show you the problem. Here is the problem. This example is example number 29.1, and this example shows that there is a building which has 7 bays in x direction which are at 26 feet, and there are 3 bays in y direction and these bays are 22 feet apart. The building itself has 12 stories. Ground floor has a height of 16 feet and rest of the floors have height of 12 feet. Altogether the height is 148 feet. Let me show you the problem description. Here is the problem description. Example 29.1, design of a 12-story cast-in-place frame shear wall building and its components. This example and the 5 examples that follow illustrate the design and detailing requirements for typical members of a 12-story building. 12-story cast-in-place concrete building. A typical plan and elevation of the structure are shown in figure 29.26 A and B respectively, which I just showed to you. The column and structure wall have constant cross section throughout the height of the building, and the bases of the lowest storage segment are assumed fixed. The beams and the slab also have the same dimension at all floor levels. This is for just academic purposes, very simple and straightforward problem. Although the member dimensions in this example are within the practical range, the structure itself is a hypothetical one and has been chosen mainly for illustrative purposes. Other pertinent design data are as follows. For example, the material properties. Concrete, it has a strength F-C, is 4000 psi. Its unit weight or density is 145 pound per cubic feet. The reinforcement is 60 ksi. Loads, the service loads are defined as follows. The live load on the floor is 50 pound per square feet, and there is an additional average value to allow for heavier load on corridor, which is 25 pound per square feet. So the total average live load is on the floors are 75 plus 25 is 75 pound per square feet. The roof load is 20 pound per square feet. Superimposed dead load is for partitions 20 pound per square feet. For ceiling and mechanical is 10 pound per square feet, and the total average superimposed dead load is 30 pound per square feet, and the superimposed dead load on the roof is 10 pound per square feet. This building is designed to seismic category D. This is very important, that the seismic category is D. It's a dual system building, that means a special reinforced concrete structural walls with a special moment frame in north and south direction and a special moment frame in east and west direction. So let me show you the north and south direction. This is the north. So north and south direction means in this direction you can see there are shear walls here and here. But in east-west direction, which is the longitudinal direction, which is in x direction, only is a frame. That's why it is said that in dual system, that means special reinforced concrete structural walls with a special moment frame in north-south and a special moment frame in the east and west direction. So let us start this model. I have used this ETABS 2016 to model this structure. Let me show you what I have done. So here is the model which I have prepared in ETABS 2016. I'll show you in detail, but before that, let us calculate the wind and seismic load over here. Now, one more thing which I should show you. In this problem, the dimensions of these members are like this. Exterior column is 24 by 24 inch, interior column is 30 by 30 inch, beams are 20 by 24 inch, the slab is 8 inch, and the wall is 18 inch. Plus there is a boundary element 32 by 32. For this simplicity, we can ignore that one. Let us take the wall as 18 inch thick. Now in this example, they say that the lateral analysis, the computation of the seismic and wind forces is beyond the scope of this example. So they have not given anything, any information about the lateral analysis, especially for this problem. So what I did, I took the case of a seismic category D structure and I calculated the forces manually. So I'm using MathCAD to calculate the wind and seismic forces. Here are the details. Now project summary, of course, is just a repetition of the same thing whatever we discussed. Here is the plan, elevation, and then design criteria. This is my standard procedure, my standard write-up. I am following the codes and standards, so ACI 31808 is used as a design code. The loads, minimum loads are defined accordingly as ASC 705 because I am using ACI 31808, so I have to use ASC 705. Based on these information and for seismic category D structure, I consider the location as in San Francisco, California, and I took these parameters from the ATC website. Let me show you the parameters. For seismic hazard, from ATC hazard, the location is San Francisco. These are the coordinates. Elevation is 51 feet. As per ASC 7, the seismic risk category is 2. Site class is D. And here are the parameters given. So these parameters are used to calculate the seismic force, like SS is equals to 1.5, S1 is equals to 0.678. Of course, they have calculated these values, which I also calculated in my calculation. And this is seismic category D. All these information which are given over here, it is repeated in my calculation. And for wind load, for ASC 705, the wind load is 85, and the wind speed is 85 miles per hour. I am not using ASC 710 or ASC 716, so this data for the time being I am not using. Maybe in another lecture I will design this structure based on ASC 716, but for the time being I am following ASC 705. Now in ASC 705, the basic wind speed is 85 miles per hour. Let me show you my calculation over here. So here the basic wind speed is 85 miles per hour, which is equivalent to 38 meters per second. Exposure category B. Occupancy is 2. Importance factor is 1. And KZT and QZ etc. is calculated over here. Similarly, for seismic design parameters, site class is D. Importance factor is 1, and SS is equals to 1.5, S1 is equals to 0.678 as I showed before. FA as per the table 11.4-1, FA is equals to 1, FV is equals to 1.5 as per table 11.4-2. Now for for the sake of completeness, I just input the values for material properties. F-C is 4000, gamma is 145, blinding does not have any impacts, steel 60,000 KSI, sorry 60,000 PSI. Now the important section here is the calculation of wind load and seismic load. When I am designing the structure for wind load, I should check the various sections of ASC 75, which one is applicable. For example, is it a simplified procedure applicable? So no, because for the simplified procedure, the height should be less than 60 feet. This height is more, so we cannot apply the simplified procedure. So we have to go for detailed procedure. So as per the detailed procedure, V1 is equals to 85 mile per hour, seismic category 2, importance factor is 1 as per the table which is here, the classification of the structure. And based on that, there is some calculation done by me. For example, wind force calculation in north-south direction, which is the y direction for ETABS. So wind load in y direction according to ASC 705, L in wind direction is equals to 68.38 feet, B is 184.33 feet. The frequency of the structure is 0.85 Hertz. The parameters, for example, G, CP and GCPI is like that. In windward direction, G is equals to 0.85, CP is equals to 0.8, GCPI is plus minus 0.18. Similarly for leeward, for sidewall and for the roof. Then based on these parameters, I did a detailed calculation in Excel and I copied over here. Let me explain over here. In the first column, the value of height is provided. Second column, KZ value is calculated based on table 6.3. The velocity pressure is QZ, which is calculated as per the formula. And for windward, leeward and sidewall, GCP values are here and the forces are the pressure is calculated over here. So here I am calculating the pressure, and then in the last these columns I am calculating the forces. So multiplying by the tributary area, I am calculating the forces over here. So based on this, when I am adding like windward and leeward forces, the net force on these stories are coming like this, 34.84, 35, etc. and etc. Why I did this? Because in ETABS it gives the wind forces at various story levels. This is a huge problem, so it takes a lot of time when I run to get the results. So what I did, I calculated and I checked, and I found that the manual calculation of the forces of various wind forces or various story levels, they are in line. I can say they are not exact, but they are in line, or they are in compromisable range with calculation from ETAB analysis. So what I can say, that in ETAB analysis the wind forces are very realistic as compared to others. I'll show you how I calculated the wind forces in ETABS later on, but let us go back to my calculation for the seismic force or for the other direction also. So in another direction, that means in X direction, the same procedure I have used, and I calculated the similar values over here. Like in this case, the wind direction, the value of L will be 184 and B will be 68.3, and these are the parameters, and the forces in the same way I calculated the forces over here. And again I found that these forces are in agreement with the ETAB analysis. So I can say I'm satisfied with the results provided by ETAB. Then what I did, I calculated the seismic loads as per the ASC 705 procedure. This is the base shear formula. This is the calculation for CS. Of course, the short period acceleration SS is equals to 1.5 and 1 second acceleration S1 is equals to 0.678. This is from USGS database as I showed before. The value of FA as per the table 11.4-1, it comes out to be 1. Just a moment, please. And FA comes out to be 1. For FV, seismic category, site class D, FV comes out to be 1.5. So my calculation proceeds like this. Calculation of SMS, SM1, then STS, ST1. As per the formula, all these values are calculated over here. And then T0 and TS, these are calculated, the short period, transition period, time period is calculated like this. Then, as per the code provisions, I have to check various things. Like for example, I have to identify type of horizontal irregularity. And as per the plan, there is no horizontal irregularity. So this section is not applicable. That means table 12.3-1, which is ASC 705 table, there is no horizontal irregularity. Similarly, no vertical irregularity, so I am not using these conditions, no vertical or horizontal irregularities. So I am also checking prohibitions based on the irregularities. Is there any prohibited area? So there is no irregularity, so there is no prohibitions. Then I have to check whether I can use equivalent lateral force method. So this equivalent lateral force procedure is permissible. This is based on the table 12.6-1 AC7. Let me show you this table. It says because the TA should be less than 3.5 times TS. And in our case, as I showed you, TS was 0.678 and TA, as I calculated below, which is less than 3.5 times TS. So as per this clause, I can use equivalent lateral force. Let me show you this table. So here is the table 12.6-1, permitted analytical procedures, equivalent lateral force or modal spectrum or seismic response history analysis. So first, the simplest way is to calculate to check the equivalent lateral force analysis. If it is allowed, we always go for equivalent lateral force, ELF method. So seismic category D, E and F. Now here is the clause. It should be a regular structure with T less than 3.5 times TS and all structures of light frame construction. So our structure falls under this category. So here equivalent lateral force analysis is permitted. So I am using this. Maybe for the sake of academic calculation, I will do the modal response analysis also, and maybe we can generate time history and we can do this analysis, but not at this stage. I am just using the equivalent lateral force analysis over here. So since this is preferred, so this is allowed, permissible, so this is the preferred procedure over here. Then I'm calculating the time period based on the formula. The time period comes out to be 0.849. Now these are the guidelines and the calculation of various parameters like the design responsive spectra. These are the functions given over here as per the ASC 7 equations number 11.4.5 to 11.4.7. So based on these calculations, the responsive spectra comes out to be like this. And based on the responsive spectra SA calculated over there, the maximum credible event responsive spectrum is like multiplied by 1.5 times TA, which is this one. Importance factor is this. So based on this, what we evaluated that this is a seismic category D structure. Because SDS is 1, so SDS is more than 0.5, so this structure falls under seismic category D based on short period response. And based on 1 second period, again this structure falls under seismic category D structure. So once it is established that this structure falls under seismic category D structure, so what we have to do, we have to go to chapter 12 of ASC 705 and we have to check as per table 12.2-1 that what are the values of R, omega and CD. That means the response modification factor, overstrength factor and the deflection amplification factor. So once we evaluated these from this table, which I mentioned here, which one is the applicable condition, like here is D3, here it is C5 because this is another direction. So all these values are here. Redundancy factor omega as per para 12.3.4.2, and as I mentioned before that equivalent static analysis is permitted as per table 12.6-1 AC 705. Then the coefficient for seismic response is calculated based on the formula given in this code. Here are the various conditions, and based on that the value of CS finally comes out to be 0.11413. The total weight comes out to be like 30,986 kip. So the horizontal force, the seismic horizontal force or base shear comes out to be 3536 kips. That means 3,536 kips, which has to be distributed on the vertically on the story levels. Then as per the conditions of chapter 12, we have to check what will be the consideration of seismic load in vertical direction. So this is the vertical case. Redundancy, as I told, it's 1.3 based on the clauses. Overstrength factor omega, these are the value of omega as per the table I mentioned before. And okay, this is very important. Determine the applicability of orthogonal interaction effects. So as per paragraph section 12.5.4, this clause is not applicable because there is no irregularity. If there will be any irregularity, then we have to apply this orthogonal conditions. But luckily, we are not considering any irregularities in any direction. This is symmetrical structure, so this clause is not applicable. The vertical force distribution is as per the formula, and this is done by ETABS. This is my old write-up, so let me correct it. Horizontal distribution, of course, is by the software. I am not doing anything. Diaphragm, yes, of course, the structure, the roof is, the slabs are considered as rigid diaphragms, and of course I will be considering the inherent torsion effect, including the accidental torsion, yes, and all these conditions which are over here we have to check. And I also checked all these conditions. Let me show you how it is checked. Like for example, design of collectors. What are collectors? Like for example, this is a shear wall and here are the columns. So the beam which is connecting the column and the shear wall, these are called collectors. So there is a condition that you have to check the collectors, and as per the sections you have to design the collectors also. P delta, of course, for concrete structures you have to consider P delta effect always. So we have to meet all these conditions which are mentioned over here. The wall anchorage, etc. All these should be mentioned. And this is all taken care of by ETABS. So let me go back to ETAB and show what I did over here. Now here, of course, first is the definition. The material definition, of course, 4000 psi material is shown, the bars are shown, 60 psi bar is used. Section property, the frame sections here, the concrete beam, let me show you. The concrete beam is 24-inch deep and 20-inch wide. Interior column, exterior column, they are used. Of course, steel beam is not used over here, so it does not have any impact. So all these sections are defined over here. For example, the interior column. The interior column is 30 inch by 30 inch. Exterior column is 24 by 24, 24 by 24. So I defined the section properties. Similarly, diaphragm, piers, etc. They are all defined. Now, coming to the very important point, that is the definition of loads. So, in ETABS, we define the load pattern. Dead load, of course, no issue, dead load is assigned. Live load is defined. Superimposed dead load is defined. Now the wind load. This is the most important factor. Let me show you how the wind load is defined. Let me delete the results so that it will be visible. Now wind load. Let me show you how the wind load is defined in ETABS. The first is exposure and pressure coefficient. There are two methods given over here. The exposure from the extent of diaphragm or the exposure from frame and shell objects. I am not selecting this second object because I am not defining the frame and shell objects. So I am taking the extent from the diaphragms. So I have defined the diaphragm here and the wind load is defined accordingly. Then wind direction and exposure. The case, all cases we have selected. Eccentricity is 0.15. Wind speed is 85. Exposure type B, importance factor is 1. KZT is 1. Gust factor is 0.85. And directionality factor is 0.85. The bottom story is the story number 1 and the top story is story number 13 because I added a small portion for designing the foundation. That means I assume that the column, the step column is 6 feet and it is buried in the ground. So the SAP ETAB will calculate it will create all the load cases which is defined over here. As per ASC cases, all the possible cases will be generated. There are 12 cases, it will be generated automatically. This is a very good advantage because we need not to define all the cases in all the directions. Just you define the parameters and ETABS defines all those 12 load cases based on ASC 705. And as it is shown over here, all the ASC cases starting from case number 1, 2, 3, 4, etc. all is used here to calculate the wind load. And of course the wind is considered in 0 and 90 degree, that means orthogonal wind is considered. So this is a very good feature in ETAB, and of course SAP also, the same features are there. Then the seismic force, how the seismic force is defined over here. In Y direction, eccentricity is only 5%. The program will calculate the time period based on the CT and X value, which is 0.02 and 0.75. Stories are from 1 to 7, and these are the responsive spectrum parameters. These are the factors which will be used over here, the R, omega, CD, and importance factor. The value of SS and S1 is defined over here. Site class is D. So when you select site class, of course, FA and FB is calculated automatically, and these are calculated automatically, SDS and SD1, which is in line with my calculation. So I am satisfied over here. Similarly, in east-west direction, which is the X direction, and X direction, the same thing, similar procedure is used. Of course, the time period is different for different conditions. So you can see this is CT is 0.016 and X is equals to 0.9, and of course the factors are different. R, omega, CD, these are values are different. On this side, SA and S1, they are the same. Then I defined the load cases. Of course, dead, live, wind, and earthquake load cases are defined. And then I defined the load combination based on the default load combinations based on ACI 318. All the load combinations are defined over here. So I need not to do anything. Let us run and see. Analyze, run analysis. Maybe we have to wait. Maybe we have to wait a little more. It's almost done. Yeah, this is done. And this is the default shape. We can start animation. This is the superimposed dead load. Sorry, this is the dead load case. So here is the dead load case animation. stop. Let us select the wind load case. The first one, apply. Let us see the animation for wind load. This is the wind load in X direction. So animation shows that the loads are applied properly. Let me show you the another direction. Stop. First step number 2. Okay. So this is the wind in north-south direction, and this is the beauty of ETABS, that we need not to define various wind load cases. It generates all the wind load cases as per ASC 705. Let me show you the seismic force. Let's display the earthquake in north-south, let's see, in east-west direction. Okay. So east-west direction means in X direction. So this is the effect of seismic force. So that means the vertical distribution of the seismic force is correct. And I checked the base shear. The base shear also comes out to be exactly the same. There is no issues. Let's just stop. And then we can go to design section. Let us design the concrete frame. Preferences as per ACI 318. All these values are defined over here. For example, the design system rho is 1.3, SDS is 1, so seismic category D. So ETAB will design the structure based on these parameters, seismic category D, etc. All the detailing will be done. Right? Let us design the concrete frame. Start. It will take a couple of minutes. So these are the design results. Let us check. Verify analysis and design. So they are matching all, no failure condition. Let us design the wall. Of course, the preferences are already defined. Same thing. Design the wall. Similarly, we can design the slab. Maybe it will take a little time. So slabs are also designed. We can check the steel reinforcement. I have already checked. These reinforcement are in well agreement with the calculation. No issues. Then we can go for detailing. Detailing preferences are okay. And we can start detailing. Okay. Now you can see the drawings are generated. This is the cover sheet, general notes, various sections, column section, column schedule. These are the beam details, beam schedules. So all these a very detailed beam schedule is there. Column layout, very detailed drawing is prepared. These are the walls, wall reinforcement. So all these details and drawings are prepared. That means we can generate these, we can convert these drawings into AutoCAD drawings, and we can generate directly IFC drawings. So hopefully it will be very helpful for you. What I can conclude now. When I used ETABS to define the wind and seismic forces, the lateral forces, I felt that these load, or the definition, or these load generators in ETABS is in well agreement with the codes, manual calculation. That means safely we can use ETABS for design of our buildings, even if it is seismic category D structure. That's why I checked that if it is a seismic category D structure, whether the calculations are okay or not. Do they meet the code requirements? The answer is yes. My feeling is that for building structures, ETABS is one of the best software. If any structural engineer who wish to use a software for building analysis and design, especially in seismic zone, it is better he should switch to ETABS. Please do not forget to subscribe my channel, and please do not hesitate to ask any question. What my future plan is, it was just a small demo to check the capabilities of ETABS, although I know that ETABS is very capable. And for other detailings, etc., and checking the loads, etc., maybe I will take a small example and I will develop another video to demonstrate that the wind load calculation and the seismic load calculations is done accordingly. And maybe I will use the same input data for responsive spectrum analysis and time history analysis, so that I can show you how the responsive spectrum analysis will be done and time history analysis will be done in ETABS. Now I have used equivalent lateral force analysis in ETABS, and the results are well in accordance with the manual calculations. So thank you very much. Hopefully you will like my presentation. Thanks a lot. Bye.